Hello everybody, it's Mrs. Avon. In video B, we're going to try some practice problems for the conservation of momentum. Now we are doing the same thing in the sublevels, but in the sublevels it's not necessary for you to write it out in the same length that you would for a textbook problem. So I want to show you a couple textbook problems. So we're going to look at one of each of the three different types of collisions that we talked about in last night's video. We're going to start out with an elastic collision. So we have two objects that are traveling towards each other that will bounce away from each other after the collision. I know that it is elastic when the objects separate after the collision. So the first thing that we want to do is list our knowns. You have to give one object an M1 and one object an M2. It makes no difference which one you use for which. Usually I call the first one M1, the second one M2. When you list your knowns for velocity, it is very important that you set a direction to be positive and you set a direction to be negative. So I'm going to say to the right is positive, to the left is negative. So V1 is 6 meters per second. Then it says after the collision it moves in the opposite direction. So that's negative 14. M2 starts moving in that opposite direction towards M1, so it has to be negative. The problem will typically not give you the sign. You have to figure it out by visualizing or perhaps drawing a vector diagram of what is happening. It is also important because it's not going to tell you in the problem to determine what type of collision it is, because then all you have to do is look on the equation sheet. There'll be three equations. If it's elastic, you copy the elastic equation, and then you rearrange it for your unknown variable. Remember that prime just means after the collision. So when I rearrange this equation, I get M1V1 plus M2V2 minus M1 V1 prime divided by M2. When you are plugging this into your calculator, if you would like to do the numerator in one step, you'll have to use parentheses and then a times sign between the mass and the velocity. You have to find the momentum first before you start adding and subtracting. So when I plug it into my calculator, I will get an answer of negative 2 meters per second, which means that it's traveling in the same direction that it originally was. It was originally traveling at negative 12, and then after the collision, it is going negative 2. So it's going in the same direction, but it has slowed down. The second type of collision that we are going to look at is an inelastic collision, which means that the two objects stick together after the collision. I approach the problem the same way. The first thing that I do is list my knowns. Very, very, very important to remember that when you list your knowns, they have to be in kilograms, meters, and seconds. So if anything, the mass or the velocity is not in one of those units, you have to convert it. To go from grams to kilograms, I simply divide by 1,000. Again, I have to determine what type of collision. When things stick together, that is an inelastic collision. So I look at my equation sheet, I copy down the inelastic collision equation, and I rearrange it for my unknown. It's asking you for the original speed of the bullet. So I have a bullet being fired into a piece of wood, and after the bullet hits the piece of wood, they slide off together. I would then rearrange this equation for V1, which is just the total momentum after, minus number 2's momentum before, divided by the mass of 1. I simply plug it into my calculator. Again, if you're going to do it in one step, I would not advise that. I would do the numerator first, with parentheses and the times sign, get an answer, and then divide by M1. When you plug all that into your calculator, and you should be trying this yourself before I reveal the answer, you should get 1.2 times 10 to the third meters per second. Again, think about, is the answer reasonable? I'm talking about firing a bullet into a small piece of wood. So yes, that's a high velocity, but it would be if you're shooting a tiny 5 kilogram stationary piece of lumber or piece of wood with a bullet. So your answers do have to be reasonable. Then the third type of collision we call an explosion. An explosion is any time the total momentum before is zero. Any type of problem. So the first thing I need to do is list my knowns. Again, it's talking about two carts being held together with a spring and a rope. They burn the rope, so when the rope disappears, the carts launch away from each other because they are spring loaded, and it initially gives you the velocity in centimeters per second, which is why the exclamation point is there. You need to change it to meters per second. And it says it's going to the left, so I have designated to the left the negative direction. Doesn't matter what's positive and what's negative, but what's important about an explosion is you'll always have two different signs. One object will always be going positive, one object will always be going negative because they explode away from each other. So when I know it's an explosion, I copy down the explosion equation. Total momentum before is zero, which means that when I rearrange it, the momentum of one is equal to the negative momentum of the other because they're going in opposite directions. Ultimately, I want to solve that for V2 prime because it's asking me for the second cart. So I simply divide by a negative M2. You never want to solve for a negative unknown, so bring the negative with you when you're dividing out the M. Again, you should practice plugging this into your calculator. Again, if you're going to do this in one step, put that in parentheses and then divide by negative M2, and the answer that you should get is 0.090 meters per second, or 9 centimeters per second to the right. You know that it's to the right because you get a positive answer, and you also know that it's to the right because V1 was negative, so V2 has to be positive. They have to be in opposite directions. Keep in mind that although we don't do problems with it, angular momentum, L equals I times omega, which looks like a W, it's a Greek letter, it's also conserved. That's why a skater, when she pulls in or he pulls in, his arms spins faster, and when he or she lets her arms out, he or she spins more slowly. So we're not really going to do equations with it, but you should know that angular momentum is also conserved.